All right, we're starting a new lecture. For the computation project, we actually still have two options, so we don't know that precisely. Yeah, so Mingyu and I are debating back and forth. So debate will be over by Monday. Alright, so we are starting a new topic, and it's called curve fitting, yes?
So this team name, just the name of the team, doesn't have anything to do with something, right?
No. I was obviously picking names that have something to do with the course structure.
So TNG Kobe doesn't necessarily do anything technical.
No. Interpret it however you like. I was at a loss how to call the teams. I didn't want to go by team 1, team 2, team 3. So I basically named them by the names of the methods that fit in the class. Or not just methods, objects as well. There are loops, there's all kinds of stuff. While loops. There's a team while loop. I was not super imaginative around midnight. Bear in mind that I was coming up with team names around midnight, so my imagination did not go wild. Alright. So, I was a little tired. So, I'm just listing things from the course. Alright, curve fitting. This is something that you will do a lot.
What lecture is this? 7?
It's 7. I uploaded the files. I uploaded the file to the lectures. So we are starting today lecture 7 on curve fitting. Curve fitting is really derivative of systems, and we will see in a moment that as part of finding a curve fit, we actually have to solve a system of linear equations. And I made that point already. More often than not, there's an underlying, like any numerical method out there, most of them have some sort of a system that is solved as part of the solution. So let's see what we actually do with curve fitting. So if you need to read, you can go to chapter 14. There's a little bit of statistics if you need it. That overview is in 14.1 and 14.2. Today we will work on linear least squares. It's also called linear regression. Okay? Curve fitting is often called regression. And you will actually have a reading assignment to do linearization of nonlinear relationships. Yes, that will be a reading assignment. It's one chapter, not a big deal. And then we will go into more general regression after that, which is in chapter 15 in your textbook. So what is curve fitting? Curve fitting is really making sense of data. Okay? So we often encounter a lot of data. Okay? So let's say that there's like a bunch of data points and you plot some property versus another. Could be permeability versus porosity. Okay? And you're wondering if you could actually formalize somehow this relationship. So it's not just a cloud of points. Can you actually say, well, there is a trend to this data, okay? And you would like to describe what that trend is. Sometimes you will actually have a functional relationship between the two properties because you derived it using basic physics. But more often than not in subsurface, that relationship is not easy to derive, okay, for the most general case. So often you're trying to kind of going backwards. Okay, I see the data. Does it make sense? Can I actually, if I find the data in this reservoir over here, can I move over in the reservoir over and apply the same knowledge from what I learned from the data that I see? So this is often from some sort of well logs or experimental measurements, and there are certain parameters that are hidden within that we are trying to unravel. And we could actually try to fit that data with a function if you are trying to go, and so these are my data points, okay? You're trying to fit a function precisely to that data. This is actually a polynomial. You will get something like this, and that's not necessarily physical, because data inherently also has noise. So you don't necessarily need to hit through every point, because that point might not be as accurate as you'd like it to be. More often, so this is called called interpolation, and as a topic is a separate topic that we will skip because, in my personal opinion, you will more often than not have to do regression. There you're just like having a cloud of points and you're looking up for approximate trend in that data. And that is called curve fitting or so-called regression.
Best fit line they call it.
Same thing. And that best fit could be a line or could be some more complex function. So if you know a little more about the problem, or you see that your data is kind of curving, you're not going to go with a line, you're going to go with something else. Okay? And we will get to that. So here are some examples, speaking of curved relationships. So for instance, this is a capillary pressure saturation curve. Do we know what capillary pressure is? If I have a core, let's say a sandstone saturated with water, and let's say that I start injecting air or I start injecting oil, as I'm displacing water, that's called drainage. So I'm displacing oil, I start from saturation of 1, so initially my core was fully saturated with water, so saturation fraction of water in my pore space is 1. And as I'm displacing water, that fraction is decreasing, right? But for that, I need to push, because my water in a sandstone is a fluid that preferentially wets that sandstone. So in order to actually get anything else in there, I gotta push, meaning I gotta apply pressure difference between those two fluids. And if I have two fluids that don't mix, the curved interface in between them actually supports a pressure jump. Okay? So you'll have a higher pressure in the fluid that is displacing this water. And as you do, you go higher, 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 higher in the capillary pressure, and you displace almost all, but never all water. Okay? And that's the joy of porous media. So it's very hard. If I had just the tube, I can always displace everything, but in a porous medium with complex geometry, no, something will get stuck in there. And that's your residual water saturation here. It could be low, but it's always there. Okay? So this is some experimental data that you see over here. And in this case, there's a model that you will mention in petrophysics when you get there, Van Genuchten model that actually fits this data pretty nicely. Okay? Not perfectly, but I can actually adjust this Van Genuchten model curve, which has certain parameters, to actually really minimize the error between where the curve actually is and where my actual experimental data point is. Second example is not so simple or nice. This is simply measurements of permeability in various sandstone cores, Fontainebleau sandstone to be precise. So this is one of the nicest sandstones out there. It's nearly completely quartz. There are barely any impurities in there, barely any clay, nothing that throws things off, okay? And it's also typically very well sorted. And you can find it in different stages of compaction. So you can find it at different porosities, and you're wondering, well, can I actually understand how my permeability through this sandstone, its ability to transmit a fluid, depends on porosity. Porosity is something that I measure in the lab. There's helium porosimeter that you throw your sample in and you find out what the porosity is. Permeability is something that I can measure in the lab as well. So I basically impose a flux through the core and literally measure how much fluid comes through per time, and from that I can back out, knowing the viscosity of the fluid I'm working with and the area of the core, I can work out what permeability is. Okay? It's stuff that I can measure. And from these measurements, there's quite a cloud of points. This is somewhere, could I do interpolation here? Interpolation, if you remember, is going through every possible point. I could connect the dots, but look at the dots. I would get something like this, right? So interpolation definitely doesn't make sense here. And this is most of the time the type of data that you're going to have from a well log. Okay? So this type of data you typically find in this case actually something curved makes much more sense than a straight line. There's no way I could fit a straight line. Well, that straight line would go this way, or that way, but it's not really a good fit. Okay? So in that sense, I do have to look at the data and see what makes sense. I can't just go fit. All right. So normally when we actually try to fit, straight fit or linear line fit will be something that is the most simplest thing. So let's learn how to do that. Okay? So I have an expression. My line is described by y is equal to a0 plus a1x. Okay? And I'm wondering which line. So based on the data, I would like to find a0 and a1. I'm looking for two things. Now, if I'm fitting a line to a bunch of data like this, then I'm making an error. Okay? So every time, so here I have this point, right? And my line is not going precisely through the center, it's a little off. And this difference I'm calling E. Okay? Here again, line is not going precisely through the center, it's a little off, so there is an error that I call E. Okay? So essentially, my error is, this is my data point minus this attempted line fit. Because for instance, x is equal to 2, my line tells me that I should be at a0 plus a1 times 2. Okay, that's my prediction based on the line. But I'm actually not there. My y value is right here. So there's a difference between the two. And this difference I'm calling error. Okay. So that's basically the discrepancies between the true value of my data and the approximate value a0 plus a1x. Okay, great. Now I'm trying to actually figure out, well, how should I go about minimizing these errors for all of the points that I have? I'm trying to kind of find the best fit that works best for all of the points that I actually see on this graph. Yes?
So the E is a vector, right?
Actually, so I have E for every point, every data point. So yes, it's a vector of values. Okay, so I evaluate E at every point that I have. Okay, great. So basically, let's look at some options. So it's a vector EI. Great introduction. Good clue. So I could just sum up all of those E's, right, and see whether I can minimize that. The problem with that is, look at this case. Okay, here, if I have just 2 data points, I could just strike a line through those data points, and I'm done. But actually, in this case, a line that is sort of a mirror image would do equally well, because this difference here is positive, this difference here is negative, and they cancel each other. So technically, formally, if I'm trying to make this 0, I can succeed in making it 0 with 2 different lines, and that's no good. So maybe we shouldn't look at just E's. Maybe I should take absolute values of those E's. Okay. So that could work, except that again, if I have these 4 points, okay, and I'm looking at the absolute values, so if I strike a line through these 2 points, okay, then the other 2, this distance plus this distance is my error. Okay. And if I take this line, then again, this distance and this distance is the error. So for the same sum of errors, I'm again getting 2 solutions. Okay? So absolute value is not working. It's better, but it's not working as well either. What actually works even better is taking the square. So if, the third option would be basically I can do the maximum distance. Okay? So I just take the maximum distance, and I take my one point that maximizes the distance, and I try to minimize that. But then the problem is that then one outlier will drive my entire trend. And I don't want to put that much weight on one point. So what actually fixes all of these cases is basically taking the square of the distance. Okay? So the square of the distance will actually, mathematically, you're better off at minimizing this sum than you are in the case of the absolute values. And it just mathematically works a little better and makes it easier to find. So what I'm gonna try to minimize is this, I'm gonna call it SR, which is sum of the squares of these errors. And again, I have some measured value, I have my model value, and my model in this case is a linear model. Okay. So my measurement is xi, yi, and I have n of them. And I'm trying to minimize difference between yi, which is actual measurement, and the linear prediction, linear model of it. And I don't know A0 and A1 right now. Yes?
Which that center sum have a square on it?
Yes, it does. Sorry. Good job. Typo. There should be a square. Okay. So let's actually do that in a very simple case of 2 points. Since it is a Friday afternoon, and I'm afraid you would fall asleep if you just write down what I'm writing, you're going to be working on your own. So when you're done, pass it on. So you're going to see a worksheet. Okay. So this actually, good point, fix that error. It's actually, I'll need to fix it. It's just, at this point, it's just a picture, so I can't fix it. So basically, I have some measured data, 2 vectors, and I have, based on my x vector, I can make a vector of my predicted values, or my model data. And I'm assuming that my SR is sum of the errors squared. This is also called least square regression. So basically evaluate what is this SR if I have only 2 points. So I have x1, y1, and x2, y2. Just write down what it is to kind of get the feeling for the formula. So basically my n is 2. Just 2 points. So that formula is for any n. Just assume that n is equal to 2. So you have the sum that goes from 1 to 2. Write it down.
Do that here in number 1.
In number 1. That's problem number 1.
We don't have different values for x1.
No, just general values. I want to actually come up with formulas that will kind of start all the time. I'm supposed to target bullshit. Yes, all right. It's like happy, yes. All right, I have a smiling bullshit right there. So what did you get?
y1 minus 0.
That's okay. Spell it out for us.
y1 minus a dot minus a1 x1 equals to a plus y2 minus a dot minus a1 x2.
True. Did everybody get that? So basically I have 2 terms, 2 of these squares in there. Great. So that's actually this SR, okay? What I know in there, so right now I don't know what x1, y1, x2, y2 are, but that's something that I know in general. It's the data that came to me. What I don't know is A0 and A1. And specifically, I'm trying to find A0 and A1, so this SR is a minimum thing. Okay. Now imagine that I have a function f of x. For the value of x, where this function has a local minimum, what do I know has to be true? Derivative of x is flat because I have a minimum. It's also true for the maximum. But this is a very positive thing. That's why I squared it. Okay? So when I have a minimum, it's not going to have a maximum. Or not an easily found maximum. Okay? So this is likely to have a minimum. Okay, so this is derivative in the case that I have only one variable. But here I have two variables. I have a0 and a1. And actually a similar is case in multivariate calculus when I have multiple variables. When I have a minimum, then my partial derivatives will be 0, both of them. So let's take a partial derivative of SR with respect to a0, the function that you wrote with two terms. This is why I wanted to have two terms. Life is a little easier to write down. Okay? And also a partial derivative with respect to a1. Okay? So write them down. What are they? You can leave it as this for now, and actually what we drive out of there, 35. Do you remember how to do a partial derivative? So if you have a square, the first derivative of that square, and then times the derivative of whatever is inside with respect to a. It's partial derivative. Do you remember how to do
Everything but a0.
a0 and a1? Yes. If you're doing partial derivative with respect to a0, you're indicating like everything else is constant other than a0. Just for this one. It's just easier to write out. But that one is you'll be able to do that, right? At the end. So we will actually have a general case. Yes? So it's amounts to
So why won't I want this up here?
It's simple. Just put the question on the
So it's literally just negative 2 times.
to both. So just to make sure that everybody knows what to do. So this was my SR for just 2 terms. Okay, just writing it down. And if I'm doing partial derivative, this is 2 times this entire expression. And then I'm doing partial derivative of it with respect to a0, which is -1 in this case, times -1. And then the same thing for this. So you will get something like this. Okay? So you can actually just leave it as is for now. And then if I do that for a1, So if you want to actually get a more general form, there was a question here. So actually this is basically sum I is equal to 1 to 2 in this case of this. And that suggests what this would look like if you had n points, right? You would have a sum that goes from 1 to n of something that looks like this. Okay? But for 2 points, I only have 2 terms, and it's just simpler to write down. Yes?
So without just taking the
Or VSR up there, yes, you could have. I'm just making it a little simpler to look at. I'm removing one of the confusions. Sums can be confusing to look at. So I'm removing a confusion. Or at least I think I am. That's what I'm telling to myself. Okay.
oh,
Yeah, you have to go through both terms. I have A0 in both terms. I'm doing a derivative with respect to A0.
why is it A9? Or, oh, never mind.
I have A0 in both of these terms, so I do have to do partial derivative of both. And then the second one is the partial derivative with respect to A1. And if I look at it, there is minus x1 here multiplying it, right? So basically, I'm going to have 2 times this entire bracket times minus x1. And then in the second term, I have 2 times the bracket and then times minus x2, right? So this is derivative with respect to A1. So this is basically what my partial derivative looks like. Did everybody get this?
Yeah.
I am going to collect these at the end as a quiz. Papers I will collect as a quiz. Motivate you to work a little harder. This is just, this more general form is just for your information. Okay? So, if I was writing this down as that sum going from 1, here it's sum from 1 to 2, but I could just extend it to n, just as we had at the very beginning. Does that make sense? Yes?
What is plus 2?
Because I have minus x1 here, and then I threw in minus inside.
Oh.
So see? Yes?
So if we're taking the
So when I'm taking a partial derivative with respect to something, that something is treated as a variable and everything else as fixed. So if I'm taking a partial derivative with respect to A1, A1 is treated as a variable, everything else is treated as a constant. So if I'm doing so none of this depends on A1 other than this. So if I'm doing derivative of this is assumed constant, right? So derivative will be 0. So the only thing that is not 0 is like A1 is my variable, so derivative of it is minus x1. And since I have a complex function, I have to, if your f of x was 2x plus 1 squared, okay? Derivative would be what? Be 2 times 2x plus 1, and then times derivative of this is 2. That's what we did there. It's just that you have A0 and A1 and sort of more general. Yes? So if you had a square of something, you gotta first do, yeah? Alright, great. So now I say that these partial derivatives, if I'm going to have a minimum, the partial derivatives have to be equal to 0. Flip the page over and set these 2 partial derivatives to 0. And that's going to give you a set of linear equations in A0 and A1. And I want you to write those down. And I want you to write them down as a matrix. AX is equal to B, or A. I'm looking for A0 and A1. So, yeah. So formulate a linear system in A0 and A1. A0 and A1 are my variables I'm looking for. So that's my vector. This is why I said that this could have been technically been, it could have been a test question, right? Formulating a linear system. Everybody's like, really? You would fail on taking the partial derivatives, right? That would be the failure.
Why are we setting them to 0?
Because that's the rule to have a minimum. Partial derivatives have of a function, of a multivariable function, have to be 0 in order to have, it's not a sufficient, but it's a necessary condition to have a minimum. Even if you had f of x. So if I had f of x, right, at minimum, my derivative, f prime of x is 0. Now in multivariate world, partial derivative of f, so if I have f of xy, then partial of f partial x and partial f partial y have both to be 0 at a minimum point. It's just that here they're calling these A0 and A1. Got it? Is everybody clear on this? Which course is that? 420 math, 427 something? Calc 2? Okay. 408D? Is it? No.
Yeah, that's right.
I don't know. 408D? There we go. If they didn't tell you, you need that stuff. There's a reason why you're. And so everything, there's some constants that I know that can go on the B side or the right hand side. So I have to have A0 times something. And then plus A1 times something. And that something might look complicated, but it's actually not. Equals to something that has neither A0 or A1.
Are we doing the generalized form or just
Generalized form. So I want those x1s, y1s in there. Because I want to come up with formula that I can use for any data.
Wait, that's a specific case.
2 points, yes. I'll be able to generalize these. No worries about it. But it's still 2 points I don't know. It's x1, y1, x2, y2, right? If you're bored, go to number 4. Don't sit idle. Not a good thing in life in general. Yes, sir. So this might first down now form second one, so I need 0 times something. And then
So if I, this is okay,
yeah, that's your first equation. So just in case you're not. So this is how your first equation should look like. So that first equation, we will have 2a0 and then plus a1 times x1 plus x2. So this is something I know it looks complex, but it's I know x1, I know x2, so it's some constant times a1 is equal to. So your first equation is a0 and a1. So now give me the second.
Do you want it in that form?
Yes, I do. This is that partial derivative of SR with respect to A0. Okay? When I set it to 0, this is what I get. This is a linear equation, right? I don't have a square anywhere. I don't have anything nonlinear. And we know everything about linear systems, right? And after the homework that we assigned, you will know even more. There were two methods that I left out last time that you will learn from the slides and compare them to Jacobi's. Just an FYI.
What?
There's successive over relaxation and Gauss-Seidel methods that are variants of that Jacobi method, and you will learn about them in your homework.
I like how it's
So that you don't feel that, you know, I left something out.
I like
I
how
know that
it's
you would be sad.
relaxed and low the other one.
Successive over relaxation. Yeah, I know that.
Over you like
It's an odd name.
It's easy then?
It's not simple. It's all about the formulas. What did you get for the second equation?
You divide out the like the x when it says like y1 x1. What do you do about this?
That's what it is. You can compute that if you know what x1, y1. Yeah. What's my next blue shirt target? I have a blue shirt target here. Did you get anywhere? Working on it. All right, keep working on it. Have blue shirts. Blue or green? How are we gonna interpret this? Blue or green? Probably green. We're green today. I think it's blue. That's blue. So what did you get as the second equation? Okay, so this is my second one. This is my second one. Okay. If I take A0, then I have x1 plus x2 times A0, correct?
Yeah.
And if I look for A1, I have x1 squared plus x2 squared. Yes? Times A1. And everything else doesn't have A0 or A1, so I throw it on the other side. So this is my second equation. Yeah? If I'm writing that as a linear system, 2 x1 plus x2, that's from my first equation, 2 x1 plus x2 times A0, 1. So A0, A1 is now my vector I'm looking for. This is x1, y1 plus x2, y2.
On the far left, the x, the a naught.
This?
No, down.
This?
Yeah, those are
So-
x's, right?
A0 times x1.
No, they just look like y's.
Oh, no. Oh, no, they're x's. Sorry. They're x. This is why I have PowerPoints for most of the class. There's a reason. Right? So then my second line in this is, so this is my coefficient here, and this is the second coefficient, so this is the linear system I'm solving, and this is a little cutoff, so scanning didn't work correctly here. So there's y1 plus y2, and there's x1, y1 plus x2, y2. So this is my matrix form. So question, in this matrix, if I actually had instead of 2 points, I had n points. Okay? Let's look at this first equation. So instead of 2 terms here, I had n of them, right? Keep going. Okay. What would this number be here? N, because I had 2, right? So I have 2. In more general case, I have n, right? And I would also have x1 plus x2, and I would keep going, plus x3, plus all the way to xn. Is that clear? Because I would get it from all of the terms here that are missing in more general case. So in more general case, here it's sum from I to equals to 1 to 2, but in more general form, I would have actually all the way to n points, right? So when I write it as a sum, I can actually suggest this is actually going to n. I apologize. So if I had n points, I would just have sums that go to n. That's all. Whereas here I had only sums that go to 2. But I'm still looking for a line that's fitting those endpoints, right? So it's still a 2 by 2 system because I'm looking only for 2 parameters. So it's easy to generalize. That's my point. But it's a little easier to write down if I have only 2 terms. Great. So this is a 2 by 2 system. I can go to MATLAB to solve it. I can go solve it by hand. I can do all kinds of things. Actually, for a 2 by 2 system, there is a formula. It's so-called Cramer's rule. Did you do Cramer's rule in your linear algebra portion of differential equations? Well, if not, I'm giving you the formula. So if you have a system like this that is a 2 by 2, you will find a number so-called determinant of A. This is how you'll find it. So it's A11, A22, minus A21, A12. This is like just a general formula. So these A's and X's do not relate to the ones we had before. And then your x1 will be b1 times a22 minus b2 times a21 divided by this determinant. So using the system that you had before, write down precisely what my a0 and a1 should be. Okay? So apply this Cramer's rule to this system here, please. And again, there's a missing y2 here and y2 here.
Where is it missing?
In what I wrote down here, but if you're using your stuff, you should be good. So just apply this Cramer rule, and that gives me the solution to my a0 and a1. I have a formula for it. Yay. If anybody is done, is there anybody done? You can try to think about how to program this. So if I give you a vector x of points and a vector y of points that are this data x, I, y, I, how would you give me back this a0 and a1 in a function called linear regression? So that's if you finished with everything. Simplified how?
Like actually multiply everything together. Like, no, I'm just saying like this. Like, do you think it's simplify that?
Oh, that's not simplifying. No, think about, well, it depends what you call simplifying. Think about using MATLAB and you have a function sum. Sum is good for you. Like that. So think about having endpoints. How would you simplify that? It's better to have it in the form of a sum. Like these here things. It's better in that's simplifying it, not multiplying everything. Because if I had endpoints, this would be a very long, that time. Don't do any further algebra. Right, so this is the, so yeah, so just plug that into like Don't. Don't. And there's a reason. Imagine you have endpoints. How would you simplify? Yeah, that would be cool. And not practical either, because you're going to use for loops to compute these sums. Or you will use some function in MATLAB, right? So it wouldn't be simplifying, multiplying everybody by everybody, and no. No. Okay. So is this clear? So I really just gave you what the solution to a 2x2 is. If you were on a computer and on MATLAB, as long as you set up the system, we had that matrix A, we had what is right-hand side B, you can solve A/B, or you can use one of your Gaussian elimination formulas or something that you programmed to solve the system. Questions? Okay. Yes, sign them please, and they're going to be valid as your quiz grade.